The next talk in this session is going to be on Yablo sequences in truth theories. This is by Cesare.
Okay, so we had a philosophical talk. I hope you are ready for another philosophical talk now. Truth and paradox, these are traditional philosophical topics. I will be interested I will investigate the status of Yablo sentences and formulas in formal truth theories. These notions, the notion of a Yablo sentence and the Yablo formula will be explained in a moment. They are derived from the so-called Yablo's paradox, which is probably well known. Nevertheless, I will remind this. So the informal presentation of a paradox. I start with that. So we consider an infinite sequence of sentences, y0, y1, and so on. And the idea is that each sentence in the sequence states all sentences later in the sequence are not true. It's like an infinite queue, and suddenly all the people in the queue are shouting, all these second-class guys behind me in the queue are lying now. That's the situation. Okay? And the problem is that we can't distribute true values over the sentences, at least assuming some natural, intuitive properties of truth. So the paradoxical reasoning assume that yk for k arbitrary is true, then yi for all I larger than k is not true, in particular yk plus 1 is not true, but also for every z larger than k plus 1 yz is not true, so yk plus 1, therefore yk plus 1 is true. That's the intuitive property of truth, after all, a contradiction. But this reasoning goes for an arbitrary k, so we obtain all yks are not true, but then yz is true, and we have a contradiction. That's the paradox. The paradox was presented initially as a paradox without self-reference. That was the main advertising point. Here, normally when you think of familiar semantic paradoxes like the liar, it's easy to see that you have some form of self-reference here, either a sentence speaking directly about itself or some cycles at least. And here, the intuition is that each sentence states something only about sentences later in the sequence, so there is no loop, there is no cycle. A paradox without self-reference. That's how it was advertised. There was much discussion about it. The issue is not clear whether it is really self-reference free or not. Okay, but let's start with the question: can we do better than that? Because this was just an informal presentation. Can we do some of it formally? Hopefully we can't do it all of that formally, because that would mean that our theory is inconsistent. I started with a definition. Y of x is a formula in a theory S with respect to a predicate T, if probably in S the Yablo condition is satisfied. Y of x, if and only if for every z larger than x not true, y of z. In what follows, I would really assume that a theory S contains enough of arithmetic to so that it makes sense. Okay. Of course, this part should be interpreted like for every z larger than x, the result of substituting the numeral for z in y is not true. That's that. intended meaning here. The Yablo sentences are obtained by substituting numerals for variables. That's the definition. Now, it can be observed rather easily that formulas with these properties indeed do exist in many decent theories. The argument for the theorem, it follows really rather directly from the diagonal lemma. I just formulated the diagonal lemma. A version with two variables is needed proved in much the same way as the version with one free variable presented usually in textbooks. So given the diagonal lemma, it's just a question of finding an appropriate phi and diagonalizing. I'm not planning to dwell on this. Okay. So the existence theorem can be proved, and now the questions which I'm going to consider. Okay. First of all, what I'm not going to consider. The question whether Yablo's paradox is really self-referential or not. How was it? I blush to say that I'm really not sure what real 100% self-reference is. So in the talk I'm avoiding this issue and I concentrate on different set of questions, different approach. I will consider various formal true theories and ask some basic question. Do these theories, true theories, do they tell us anything substantial about Yablo sentences? In particular, are Yablo sentences provable or disprovable in true theories? Are they probably equivalent in proof theories? That's really the question. The second question, it's about one implication. If for all z larger than, say, 5, y of z is not true, then for all z larger than 100 also. This implication is trivial, but the opposite implication. What about this? Are they equivalent? Now, the next question, comparing Yablo sentences with the liar. Are they probably equivalent to statements of their own proof? Do they have liar property? That's the question. Question 4 is not really a separate question, it's just caution. To what extent does the answer to this question depend on a particular choice of a formula y of x? Because we have specified a general formal condition which a formula must satisfy in order to be called a Yablo formula. But various formulas can satisfy such a condition with perhaps very different properties. Okay. Now, just to clear the ground, just a simple observation. We can consider a theory PAT. PAT is not a true theory. It's we just extend the language of Peano arithmetic PA with a new predicate T, but this predicate is nearly ideal. There are no specific axioms governing its use. Then it's rather easy to observe that PAT doesn't prove that something is Yablo, it doesn't prove that something is not Yablo, and Yablo sentences are not probably equivalent in PAT. Very simple model theoretic argument. Now, the real question is what happens when we start adding proof axioms. Axioms governing the use of the proof predicate.
Does a T occur in the induction
Sorry?
Does the truth predicate occur in the induction?
It doesn't matter.
Okay.
Yeah, that's it. For this, it doesn't matter. Extended induction changer, nothing here. Okay, so what happens when we add truth axioms? I think it won't be surprising when I say that the answer depends on the choice of the truth axioms. I'm going to consider two systems, two truth systems. One will be theory FS, Friedman-Sheard theory, and the second system, critical axiomatic theory of truth. Both theories belong to a group of so-called untyped truth theories. Very roughly, it means that they permit in a reasonable way applications of the truth predicate to sentences which themselves contain the truth predicate. So no divisions like classical object language, meta language, just one language with the truth predicate. I consider only those theories because the questions, the same set of questions with respect to typed truth theories is not very interesting. So the first rather well-known system, Friedman-Sheard system. In FS, it's a very nice system. When you look at the axioms, they look so familiar. I mean, they're just standard compositional axioms. Disjunction is true even though if one of the disjuncts is true. No surprises, only all of these goes for all sentences of the language with the truth predicate. For extended language. No axiom for atomic formulas with the truth predicate is on the list. This is compensated by adding two rules. They are usually called necessitation for necessitation, terminology borrowed from modal logic. So as soon as we obtain phi as a theorem, we are permitted in the next move to derive phi is true, and the opposite from necessitation. That's the axiom system.
Sorry.
In FS,
Can I ask a question?
yeah.
Could you just comment why the right hand rule is a rule and not an axiom, right? The connect there. So why isn't it for the connect rule there? Right, this one. So why isn't it, for example, T phi implies phi? Why is it T phi from T phi derived phi? I can see the point in the necessitation rule, of course, that the necessitation rule must be about theorem or validity, I understand. But why isn't it an axiom there? On the right-hand side, the connect rule.
The connect rule.
Yes. Why is it a rule? Why is this stipulating theorem and not just local truth as you have it in the truth axiom, right? For example, if you have epistemic logic, right, you have H and A knows phi then phi.
Yeah, I'm not.
Right?
I'm not sure at the moment.
I see.
I mean, there are certainly you can't add a condition, a general condition for atomic sentences with the truth predicate as a biconditional, because you obtain an inconsistent theory. I'm not sure how it is with relations. Anyway, the results, an overview, what happens in FS. In FS, it turns out that all Yablo sentences are probably equivalent. Moreover, we can obtain this result in a uniform manner with variance as a general statement. Also, as soon as we have this, a simple application of necessitation and composition of axiom guarantees the first corollary. It's also easy then to obtain the information that each Yablo sentence is equivalent to the statement of its own untruth. In FS, well, Stephen Yablo is not here, so I can say FS thinks that Yablo is a liar. Moreover, if FS is consistent, then neither the existence of x such that y of x nor the existence of x such that not y of x is a theorem. So these are independent sentences. All these arguments in case of FS are rather quick. A more interesting example now, the second theory, Friedman-Sheard theory KF. This is KF is an attempt at axiomatizing Kripkean notion of proof. The advantages. One advantage that the theory has natural axioms. I will not read all of them, just I will give some intuition at the moment. The second advantage, the theory has a very natural semantics. As for the axioms, it's useful to think about it in the following way. We can define the notion of falsity. A formula is false, let's define it. It means that the negation of this formula is true. Okay? So now, with such a notion of falsity, we can appreciate that the axioms of KF are in pairs. We have an axiom for truth. We have an axiom for false. Conjunction is true. The axiom number 4 specifies under what conditions. Conjunction is false. The axiom number 5 specifies under what conditions. In this type. Sometimes, in some versions, KF is even formulated with two primitive predicates, truth and falsity. Now, additional axioms are often considered, consistency and completeness. The axiom of consistency states that no sentence can be both true and false. So the axiom of consistency excludes truth value blanks. The axiom of completeness excludes truth value gaps. It is known that we can add consistently to KF consistency or completeness, but not both. Some facts about KF, which I use later. KF with consistency implies the throughout direction of the Tarski biconditional. KF with completeness implies the truth in direction. So I guess it is known that you can only direct the direction, so it illustrates nicely that you can have both consistency and completeness in the direction. Now, KF is a classical theory, a theory in a classical logic, but it was designed as a formalization of a partial approach. The models of KF are classical, but such a model can be turned into a partial model. You can define a partial model given the model of KF. Just define extension as the set T and anti-extension as the set of all Z's, such that negation of Z is to the extension. And then you can have a partial model, and you can have a strong linear satisfaction in partial models. Just a reminder. I mean, it's a standard definition. Strong linear satisfaction. Now, facts about KF. Truth is well behaved. If we have a model of KF, then given an arbitrary sentence, phi will be strongly linearly satisfied in a partial model determined by the initial model, and if and only if phi is true, will be it should be strongly linear on the right side as well in the criticism. A notion of a dual model comes next. Given a model of KF, we can define a dual model. Just define T dual interpretation of the truth predicate, as a set of all those sentences which are not in the anti-extension. This can indeed modify the initial interpretation. A sentence can be indeterminate initially. And properties of dual models. If we start with a model of KF, then a dual model will be a model of all the axioms except KF. The last one was for negation of truth. But if we assume in addition that the initial model satisfies consistency condition, stronger than in case A, then the dual model will satisfy full KF with completeness. So that's the method to obtain models for completeness. Models for consistency are obtained by performing Kripke's fixed point model construction. And then you can take a dual model to obtain models for KF with completeness. Okay. Now, when we consider what happens with Yablo formulas, various questions can be asked. The big question is which theory we take as basic. For example, we can ask what happens if a formula y of x is a Yablo formula in KF with consistency. Then, in such a case, the answer depends on the choice of the formula. So the answer is, unfortunately, various things can happen. I just give an example of two formulas such that both of them are Yablo formulas in KF with consistency, but KF with consistency proves one of them, y0, and but it proves the negation of y1 of them. The proof, the construction essentially uses the fact that L, the liar sentence, is a theorem. It is provable in KF with consistency. So that's the peculiarity used in the argument. So you can use the liar itself to produce a sentence in given properties. The case of KF with completeness is not symmetric in the sense that the result doesn't depend on the choice of formula. The result is that KF with completeness proves uniformly the negations of all Yablo sentences. The next question, what happens if y of x is a Yablo formula in KF itself without any additional axioms like consistency or completeness? So the Yablo equivalence, let's assume now it is provable just in KF. Then the result is that KF with consistency uniformly decides Yablo sentences, but in the opposite way than a theory with the completeness axiom. Indeed, it turns out that if y of x is a Yablo formula in KF itself, then KF with consistency will treat every Yablo sentence as a liar. So it's still a liar in KF with consistency. The question, the remaining question is whether anything can be proved in KF itself. Because all the previous results which I showed, this was an information what happens if we use additional axioms, like consistency, like completeness. What happens if we are not permitted to use them? So work just in KF. And assume that y of x is a Yablo formula in KF. I don't have a general answer. I have an answer for a rather special case, but this special case covers Yablo formulas obtained by diagonalization. So the standard construction of a Yablo sentence is covered here. The additional assumption is that these Yablo formulas are well behaved in partial models. So when we take a partial model, y of a is strongly insatisfied if and only if the right side of the Yablo condition is strongly insatisfied. It is not true in general that if a biconditional is provable in KF, then it will translate in this way to partial model. So some caution is needed. In such a case, the information is really that all Yablo sentences are uniformly equivalent. So when we consider a specific formula constructed by diagonalization and ask about this specific formula, what happens in KF, this is what happens, equivalent sentence. And summary, so it's just a list of the result I sketched in this talk. All Yablo sentences are probably equivalent in FF. They are also liar-like. KF with completeness proves uniform negations of sentences, which are KF plus completeness. In KF with consistency, various things can happen. But KF with consistency proves uniformly on Yablo sentences by Yablo in KF. And they are also liar-like. KF doesn't decide sentences which are Yablo in KF, but it proves the equivalence of Yablo sentences which are well-behaved in partial copies. The most important slide.
I have a problem with the very beginning of the story, so maybe I'm confused. Can you go back to the first slide where you define this? No, the previous slide. Yes, here. So, as far as I can see, you define each one of these sentences in terms of the others, and so I'm not sure. I mean, this is to me not well-founded definition, so I do not understand how this defines them. But then, even if it does, so to make them sentences in a formal language, you need some Yablo enumeration to lift the index set into the argument. And so I do not see what guarantees that there is a recursive enumeration of these sequences.
Okay. First, this slide was not a definition. Okay. On this slide, this slide was an informal presentation of a paradoxical reason. Okay. When we want to transform it into a formal reasoning, well, indeed, we need to do something. One proposal, just a moment, one proposal is to go via diagonalization. This involves some decisions. There are some differences when you compare it with the original formulation. One of the differences is that you don't have these indices anymore. Instead of indices, we have just a moment. I wanted to show this one really. Here the decision is that instead of indices, we will have numerals occupying the place of a variable. So x here is a variable. And the formal construction is a construction from a diagonal lemma. It was not the first slide, it was just an informal description.
So what implies the existence of such formulae? This is some sort of allegedly implicit definition, but I don't see how it justifies that such formulae exist.
No. This is just a definition. This is an explanation of what we understand by a Yablo formula. For existence, we need a theorem, of course. And just a minute.
Sorry, you might have said all this, but
yeah. If we take a sufficiently strong theory, a theory which contains enough arithmetic, we can construct Yablo formulas by diagonalization.
Sorry, I missed that theorem.
Yeah, okay, this is the existence theorem.
Yeah, so who?
Yes.
Me, okay. So I just wanted to have another suggestion of how you can get such a sentence. You could go to a logic which doesn't have a compartment structure, like L omega 1 omega 1. So that I think we should take.
Yeah. Or you could use set theory with some anti-foundation axiom.
Just as
CFA.
Just a small comment to a question which was raised before, why we have this introduction or elimination rule for the truth predicate, which was true or phi, then implies phi. And we have it as a rule and not as an axiom. And might it be the case just because the Friedman-Sheard in the paper, they consider lots of maximal consistent truth theories. So if you formulate this as an axiom, you fix it. But if you formulate this as a rule of inference, then it covers all kinds of new material that you might consider. And they indeed consider many such systems, yes.
Just back quickly on this point, it's that Montague proved a theorem. Montague proved a theorem in the 60s, which shows that any extension of PA formulated in the language with truth that's closed under if phi is provable, then true phi is provable, is inconsistent with the axiom version of co-necessitation. And also, you can prove the same thing that if you have,
I think you are.
That's why you do.
Yeah. Mhm.
Okay, I think we should move on to the next talk. Thanks, Cesare. Next talk is titled Moving Up and Down in the Generic Multiverse. It will be presented by Benedict.
So, thank you very much. I just noticed while I was going up here, maybe it would have been better if Nona's talk is first before mine, because I'm not going to say anything about what forcing is, and I think she might, right? Okay, so those of you who have no idea what forcing is, keep in mind that during the next talk you will learn what this is. It's very fitting that I'm giving this talk here, because there is some ICLA history involved. Joel Hampkins was an invited speaker at ICLA 2009, and Joel gave a talk here called Some Second Order Set Theory, which was a survey talk in which he talked about our results on the modal logic of forcing, and some other results involving the ground axiom, the bedrock axiom, and other things, stuff that he has then called set theoretic geology. And I think in some sense, this survey talk, which he probably has given in other places as well, not just here at ICLA 2009, was one of the reasons for him to develop a new foundational theory of how we should look at the foundations of mathematics. He wrote a paper published in the Review of Symbolic Logic called the set theoretic multiverse, where the notion of the set theoretic multiverse is not new to Joel. This has been around for a while. But he very strongly pushes the view that if you want to stick to mathematical practice, you should not insist on finding the true universe, but instead you should find out what is going on between the different set theoretic universes. You should understand the various construction methods that allow you to go from one universe to another, and what really matters is the truth that lives in this multiverse. In fact, he is interested in the full multiverse, not just what we'll be talking about today is the generic multiverse, where you just look at forcing. The most general version in Joel's setup is that you look at all possible construction methods, set theoretic construction methods. So you have, for every construction method, you have an accessibility relation, and you have a huge multimodal Kripke frame, where the individual worlds in the Kripke frame are models of set theory, and the relations are the various construction methods that allow you to move from one of the models to another. However, we will not look at this general multiverse, but we will look at the generic multiverse, where we only look at one particular construction method and its inverse. There is a quote from Hugh Wooden: the generic multiverse is generated from each universe of the collection by closing on the generic extensions, enlargements, and on the generic refinements, inner models of a universe which the given universe is a generic extension of. And this is a notion that Wooden used, and in particular the notion of truth in this generic multiverse is a notion that Wooden used, for example, in his work on the continuum hypothesis. Because one of the things he's interested in is logics that are invariant under forcing. And for that, you need something that, no matter where you go by forcing extensions, things still stay true. So this is the understanding of the generic multiverse is a crucial part of the Wooden program. Okay, so let's make this slightly more precise. We fix a universe of set theory, your favorite one, and we iteratively build all set forcing extensions and ground models. So set forcing extension, as I said, I will not say what this is. You will learn this in about an hour. And the ground model is just the inverse. So an inner model of a given model of set theory is a ground model if in that smaller model you find a partial order, and in the bigger model you find a generic subset of that partial order such that the generic extension is the original model. So it's really just the inverse of the set forcing extension relation. So this naturally produces a cryptic structure that we call GM for generic multiverse, and you have these worlds, the models of set theory, together with an accessibility relation that goes upwards. These are the forcing extensions, and the inverse relation that goes downwards. And these are the upwards and downwards from the title of the talk. And of course, because they are inverses of each other, the bimodal logic is something that should probably look a bit like temporal logic. The general aim of this is to understand this bimodal logic. This will depend, of course, on the model of set theory you started from. So obviously, if you change the V, then you will get different logics. But one question is, which are the possible values? And can you say something about that? In particular, can you prove theorems about them that allow you to understand something about the powers of particular set theoretic construction methods? I will give an example in a moment. Okay. Now, let's define a few things. So we start with the standard language of propositional modal logic. We have a countable set of propositional letters. We have two modal operators, one going up and one going down. We have the monomodal languages, and we have the bimodal language that has both operators. On the other side, on the set theoretic side, we have ordinary first-order language of set theory, and that has its sentences. So in order to make our multiverse into a cryptic model, we first need to find out what truth means, and truth of modal statements has to be somehow linked to the sentences of set theory that are true in the various models. So what we do is we take an interpretation that assigns propositional letters to sentences of the language of set theory, and then each interpretation tells us which propositional letters are true in which model of set theory, namely exactly those that if you interpret them as sentences of set theory by that interpretation, you get a true statement. So this is a cryptic model, and the accessibility relations will correspond to the two modal operators. So we call a function a translation if, well, at the bottom level, at the propositional level, it comes from an interpretation as we have just defined it. It behaves appropriately with the propositional connectives, and I guess this is a pointer. And the upwards modality is interpreted as the sentence stating for all forcing extensions M, we have that the translation of phi is true in M, and for the downwards modality, this is interpreted as for all grounds M, we have that the translation is true. Now, these are natural language statements, of course, but by magic, or sometimes called the forcing theorem, this is actually something that can be expressed in the first-order language of set theory. So in the case of the upwards modality, you use the forcing theorem. In the case of the downwards modality, you use a result by labor that the ground model is definable in the forcing extension. So these translations are actually translations into the language of set theory. And you can, if you want to, you can remove all of the modal stuff, and it becomes pure set theory. Then the modal logic of the generic multiverse is the set of all bimodal formulae such that for any translation, that means, so every translation is determined by the interpretation that assigns set theoretic sentences to the propositional variables. So for any translation, the translation of phi is true in V. And of course, you can look at the two fragments, the fragment of the modal logic of forcing, where you only look upwards. So you start from a model and only look at forcing extensions, and the modal logic of grounds is the dual where you only look downwards. Now, as I already said on my first slide, Joel was reporting in 2009 on a paper that we had written in 2008, where we determined the modal logic of forcing. So this is this second fragment that we understand to some extent already. So this is the paper, the modal logic of forcing, published in 2008. So in this paper we observed two things. Well, we observed one thing and proved another. First of all, this modal logic of forcing is always within a very, very small range of modal theories. Namely, it is sandwiched between S4.2, which is the modal logic of directed partial orders, and S5, which is the modal logic of equivalence relations. So that is in fact true for no matter from which universe you start. And the theorem then was that we proved for one particular model of set theory, namely the constructible universe, that takes the lowest possible value as 4.2. Which then, in turn, proves that if you don't look at the modal logic of forcing, for a particular model, but you look at all of those statements provable in ZFC, then of course this has to be exactly as 4.2. Right? Because it's the intersection of all of these, and we have one where the lowest value is obtained. I don't want to say much about how we proved that, but a little bit. So what is very central to the proof of this theorem is our notions of control statements. So there are various control statements with which we can say something about how the modal theory behaves. The most important one, and the only one I want to talk about in this talk, is the notion of a button. A button is a sentence that there's a modal version and a set theoretic version, and they easily translate back and forth. This is the set theoretic version. A sentence in the language of set theory is called a button in V, and we call it unpushed if it is false in V. And we call it a button if there is a forcing extension where it becomes true, and from that point onwards it will stay true in all further forcing extensions. So that's a button, and it's unpushed if it is not yet true. And in a sense, unpushed buttons in models of set theory measure where we are in this interval. So you are somewhere between S4.2 and S5, and the information about how many unpushed buttons are around tell you where you are. In fact, the statement, the modal logic of forcing is equal to S5, is actually equivalent to there are no unpushed buttons anymore. So that is something that you can replace this by, and for the modal logicians that is not terribly surprising, because if you think of what S5 is just diamond box P implies P. What does that mean? Well, diamond box is something like a button. It's something that can be possibly made necessary. And diamond box P implies P says everything that can be made possibly necessary is already true. And that's exactly what it means to push a button, right? A button is something that is possibly necessary, and it becomes pushed when it becomes true. Okay. Now, here's my example of how you can use theorems like this in order to understand something about the power of certain tools. This is a theorem that Joel had actually proved before we went on to even tackle the problem of the ZFC provable modal logic of forcing. He proved that if ZFC is consistent, then ZFC plus the modal logic of forcing as S5 is consistent. This is an axiom that he called the maximality principle, MP. Now, from our result, we can prove that you cannot prove this result by a forcing argument. So this is a theorem that requires some component in the proof that is not a pure forcing argument. And that follows from our main result. So that this consistency theorem cannot be proved by forcing alone. Here's the proof. Suppose you could. So suppose ZFC proves there is a forcing extension in which the modal logic of forcing is S5. Well, then in that forcing extension, the modal formula, diamond box P implies P is true, right? That's what S5 means. But that means that in the original model, so if you don't go to this forcing extension, diamond box P implies P is true, right? But since V was arbitrary, this must be a ZFC provable modal formula, but it's not a theorem of S4.2. And that contradicts our theorem. So it's a very simple thing to see that there is no proof that allows you to go from one model to another with a set forcing extension that will produce this theorem. And in fact, Joel's proof is different. So what you need some argument that involves a compactness argument. You construct a particular model of set theory, and then from there you do a forcing. And together, of course, this is possible. So this is still motivation. Why it is interesting to prove these abstract theorems about modal logics of forcing, because they do more than just tell us something about the modal logic of forcing. They tell us something about what we can do if we restrict our attention to particular proof methods. Okay, so now let's go to the modal logic of grounds. This is slightly small. This is just a reminder what we had proved for the modal logic of forcing. So the modal logic of forcing was sandwiched between S4.2 and S5. Now, for the modal logic of grounds, we easily get that S4 is a subset of the modal logic of grounds for any model. However, directedness is an issue. And here is a statement in the set theoretic language that we have no clue how to prove, and that is the obstacle here. So if you have any model of set theory, and you take any two models, what do I call them, M and N, and these two models both make V into a forcing extension of themselves. So there is some partial order in M and some partial order in N, and you can generically create V in two different ways from M and N. Then the question is there some inner model that is contained both in M and N, such that there are partial orders in that model that produce M and N? That is directedness. And we have absolutely no idea whether this is true in general in set theory. Some people have said no. Some people have tried to refute it. No one has succeeded so far. In fact, we can give this a name, so we can make it into an axiom, and we call it DDG, the downward directedness of grounds hypothesis. And in fact, in all universes where we can determine the truth value of this thing, it is true. That doesn't say anything, but at least we have no counterexamples so far. So this means that we do not get S4.2 as the lower bound, but we have to stay with S4 for the moment. Now let's talk about the upper bound. The upper bound, of course, cannot be an upper bound for grounds either, because if you start in a model that is the minimal model, like L, the constructible universe, well, then everything that is true in all ground models is already true in L. So what you get is that the modality trivializes. Truth and necessity are the same in L. So we call this propositional logic because, well, the modalities are gone, the modalities are, you can just ignore them. And in fact, any model that is not the forcing extension of anything else, these models are called models of the ground axiom, these have the property that the modal logic is pure. So what we get as a summary is a much weaker upper and lower bound, S4, and then this very, very strong modal logic as the upper bound. Okay, so that already looks somewhat less optimistic than before to get any results. So let us see, well, we can't really deal with the point 2 issue, because this is, as I said, a very difficult set theoretic problem, and we have no clue how to attack this. So that means we are not going to provide any examples of models where the modal logic is exactly S4. So let's try to deal with the S4.2 case, and in fact we can prove that if ZFC is consistent, then there is a model such that the modal logic of grounds is S4.2. And this is done by a model called the bottomless model by Jonas Reitz, a PhD student of Joel's, who, in order to look at this ground axiom that I mentioned on the last slide, and to show that the ground axiom is in fact consistent with not being a minimal model like L, he produced the bottomless model where, even though you can always find further grounds, you can never find a last ground. So you can check. This model is a class forcing extension of L, actually a cardinal preserving class forcing extension of L. That will become important in the next slide. You can easily check that this does satisfy the downward directedness of grounds hypothesis, and you can also very easily check that it has infinitely many independent buttons, which is what our proof needs in order to show that it has the modal logic of grounds is S4.2. So this means that the ZFC provably valid principles of the modal logic of grounds have to be sandwiched between S4 and S4.2, and they are exactly S4.2 if someone manages to prove DBG. Okay, good. Now, this has not much to do with the original aim. You remember what the aim was. The aim was to find out what the bimodal logic is. And now we looked at the two fragments. So, in fact, we know hardly anything about the real bimodal logic. So as soon as the modalities mix, we don't really know much about the fact that you trivially get out of the fact that they are inverses of each other. What we try to do instead is to look at combinations that are possible if you look at the upwards and the downwards modal logic. So we know that the upwards modal logic can be S4.2 and S5. So the question is, which of these four possibilities can actually occur? So, and I deliberately didn't say which is which because it will turn out that this matrix is symmetric, so it doesn't matter. Can you have S4.2 in both directions, or S4.2 in one and S5 in the other, or S5 in both directions? Well, the first observation is S4.2 in both directions is very easy because you just look at the bottomless model again. And because the forcing, where we already know that it has downward S4.2, and because the forcing was cardinal preserving, the entire arguments that we gave in the modal logical forcing paper will still work, and therefore you can show that this also has S4.2 upwards. Okay, that was easy. So we have one yes. The two mixed versions are variations of this together with the theorem that I briefly sketched, Joel's theorem of the consistency of S5. To do it the other way around, there you just do the original construction. There is a very mild large cardinal assumption here that is needed in order to get the forcing construction going. If someone is interested, then you can try to prove this without that. It's not a strong assumption. We don't know how to do it without that. Okay, so this is what we get. And there is one question mark left, and I would like to end this talk by showing that that question mark is actually a no. So it is not possible to have S5 in both directions. So this is a theorem. And there is no model of set theory such that both its modal logic of forcing and its modal logic of grounds are S5. And the proof is relatively simple. It's so simple that it fits on the remaining space of this slide. So you sit in a model of set theory, and you look downwards into your grounds, and when you go downwards into the grounds, things that you think are countable could become suddenly uncountable, right? They could become cardinals, because it could be that you were created by forcing that collapsed these things. So let us call an ordinal, a countable ordinal, a ground cardinal, if there is a ground in in which alpha is a cardinal. So we call gamma the least infinite round cardinal, and that obviously has to be less than omega 1, because omega 1 is a cardinal in the universe you're living in. The statement gamma is equal to omega 1, which tells you that there's no ground below me that believes that some countable ordinal is a cardinal, that is a downward button, because the moment you reach a ground where this is true, if you go any further, then of course these models get smaller and smaller, and therefore it can't be that suddenly there you have other ground cardinals. But the negation, the smallest ground cardinal is omega 1, is an upward button, because you can make it true by just collapsing omega 1, and you can make it false and the negation true by collapsing omega 1, and then it will stay true for all forcing extensions, or false, but depending on what you talk about. So you have a statement that is a downward button and the negation of an upward button. So that means if you have a model where both the upwards and the downwards modal logic are as 5, that means all downward buttons and upward buttons are true. But that can't be, because the S5 downward will give you that it's true, and the S5 upward will give you that it's false.
How is this statement obtained?
Which?
This gamma equals omega 1.
What do you mean by obtained? I typed it in. What precisely do you mean by obtained?
The idea that that statement would work.
Do you have any method to arrive at this step? Do you have a method to arrive at this step?
For example, it is true in L. Right? It's true in any model that has no grounds. But this is not very important for this, right? Because you only have to show that. Okay, that was the end of the proof, and that's the end of my talk. Thank you.
I actually am not asking a question as reflecting a kind of puzzlement. Because when we, for example, prove the Gödel completeness theorem, right, then it says if I have a consistent formula, or in the Henkin version of consistent theory, then there is a model. Now, one can ask the question, what exactly does there is a model come from? And that question is not troubling, because it turns out that the Gödel completeness theorem can already be proven in arithmetic. Right? Now, here when you say there is no model of set theory such that blah blah, then the point is set theory is supposed to furnish us with what the word model means, but now we are talking about models of set theory. So it's almost like saying, is the US Constitution constitutional? And we don't understand that question, because is something constitutional is asked within the framework of the Constitution, and now to ask whether the Constitution is constitutional creates a kind of puzzlement, which somehow you and advocates do not have, but I do have.
Well, I mean, if you are worried about this in this particular theorem, I think it might be slightly more difficult for the other theorems.
Yeah.
But you could just think of having some background set theory that does provide you with a word model, and then you prove it in that background theory, and then this model of set theory, if you want, can even mean set size model of set theory, which weakens the theorem, of course, but it's still true, right? The theorem would be there's no set that satisfies all of the axioms of ZFC and, in addition, satisfies these things, and that's provable. If that makes you less worried.
Not really, but no, because let me rephrase the question in a different way. Supposing somebody to ask the question, what does the word human mean, right? And then the answer is, a human being is any mammal that lives inside Eurasia, which speaks, which uses language. And then somebody could say, no, a human being is any mammal living in the Americas who does this, etc. Then one could say, why not make them all human beings, right? There would be no difficulty. But somehow it seems like these different notions of different set-theoretic universes can't live with each other. And our notion of set is that it should be inclusive notion, So that if V1 is a model and V2 is a model, then the union should be a model.
Well,
and somehow
I would say this is exactly what Joel wants to go against with his, his multiverse view. This is, of course, what people in Foundations of Mathematics have said over years, that there is what Maddie calls the maxim unify, and that unify is the most important maxim, and would even, her favorite maxim is, of course, maximize, and she would say unify would even trump maximize. And I think what Joel in his paper wants to say, no, on the contrary. There is no unify. What we want to understand is really the whole range of these things, and it doesn't make sense to think of the, to use the modal phrase, the Kripke model of the multiverse as a pointed Kripke model, but you want to just see it as a Kripke model.
I see. Thank you.
I just want to comment on unify. I think unify is very unreasonable because even in small models like models of first order logic, unify doesn't hold. You take the union of two linear orders, you no longer have a linear order.
Well, I think in Maddie's work, unify was very strongly influenced by the cabal view of what set theory should be like, and this idea that there is the linear order of all large cardinal axioms.
Can I respond to her? I
Please do.
think what she says is very, very important, because it's in a way clarifies my question. Because suppose we also have the axiom, no two human beings can live on different sides of the Atlantic. That would prevent human beings that would make sure that if there are human beings in Eurasia, there can be human beings in North America. So her question would be answered by saying, yes, the union of two linear orderings can't be linear ordering, but it is still a relations. So relations do live in a world in which you can add those things. And I would have thought that sets would be like relations and not like linear orderings. And it's this tension. I think you understand my tension.
I recall Malfitting spoke on intuitionistic logic and forcing. If I remember well, he find Kripke models in terms of the for intuitionistic logic in terms of the forcing extension. So can you relate your model logical forcing to that by Yablo's translation?
We have so I've also looked at these things, and we have tried several times to really understand the relationship between looking at the there must be some relationship. Let's say it that way. There are some theorems, for example, the theorems that Bob Lubarsky has proved on constructive set theory that use Kripke frames in a way that is so similar to what this multiverse looks like that it can't be that there is no connection. But I don't really understand it, and I have asked many people.
So you have a non-constructive claim. It can't be the case that there is no.
Yes.
I just have a comment on Rohit's first point on the idea of looking for sets, models for set theory. There was a paper once by Jerry Adamek. It was titled, "Is Algebra Algebraic?" Thank you very much.